Hello, my name is Andrew Zhao. I'm a postdoc at Sandia National Labs. In this talk, I will be presenting this paper entitled Learning the Structure of Any Hamiltonian from Minimal Assumptions. If you're interested in the full paper, you can find it at this archive link, or simply scan this QR code. And if you have any further questions, or you want to reach out for further discussion, please feel free to reach me at my email here. So, in this talk, we're going to discuss the problem of Hamiltonian learning. What is Hamiltonian learning? Well, imagine you're given some unknown n-qubit Hamiltonian, say written in some decomposition into some Pauli operators with some coefficients lambda. You're asked to infer or learn these Pauli operators and their coefficients lambda. Namely, in this model, we're going to consider querying real-time evolutions of the unitary operator that generates the dynamics under this Hamiltonian. And you're tasked to learn these parameters up to some controlled error epsilon. So for example, you might imagine this model on the left here, which is a system of qubits that are, say, connected on this sort of hexagonal lattice. Between each of these qubits on the vertices, you might imagine, there's some interaction. That's, say, an XX interaction or a YY interaction, something like that. And you're told this structure, you're told this hexagonal structure, and you're asked, what are the strengths in between each of these qubits? So in order to access this kind of Hamiltonian, an experimental model might look something like this. You're given access to input probe states rho. You're allowed to apply, at certain times, this unitary operator that generates the dynamics of your unknown Hamiltonian. And you're allowed to interleave these what we call control unitaries, V's, which are really just experimentally controllable, 1 and 2 qubit gates that the experimenter can interleave between applications of the unknown unitary. And then you measure at the very end. Without loss of generality, we can imagine this measurement just being a standard basis measurement because we're allowed to, say, rotate the measurement basis with this final VL. So this has been coined the discrete quantum control model, what we'll call essentially the conventional access model, called so because this is essentially what experimentalists have been doing and continue to do for many years, essentially since the advent of quantum devices. But this terminology, discrete quantum control, was coined by, I'd say, these authors here. So what is structure learning? In structure learning, we essentially take away, as the title, as the name might imply, the structure of the Hamiltonian. So we're given the same task as before, but now we're not told what the EAs are. We're not told what the Pauli interactions are in between these qubits. And in fact, it's not even necessarily that we know like the interaction graph of this Hamiltonian. We might in fact have more than 2 body interactions, but like 3 or 4 body interactions. We might even have interactions that span like non-locally in the sense of this interaction graph. Indeed, there is no interaction graph, we assume, underneath these qubits. So now our goal is not only to learn the coefficients, the lambdas, but also to learn the terms themselves. What are the interactions between these qubits? So in the quantum version of this problem, it hadn't really been studied until this paper that appeared in Fox last year by Bakshi, Liu, Moitra, and Tang, where they initiated the study of this kind of a question. How can you learn the structure of a Hamiltonian from its unitary dynamics? And we'll talk a bit more about this later. One of the nice things about structure learning and why it's practically important is that it allows you to catch, say, unexpected interactions between your qubits. Even if you have some pretty decent prior assumption about what your Hamiltonian is, in the lab, you might have various spurious effects that occur between the qubits that you had no idea about, and you would like to catch those interactions. You'd like to be able to learn those interactions if they're significant without having to know that they exist in your system in the first place. So that's one motivation for the problem of structural learning. Okay, so in this BLMT algorithm that I referred to previously, they solved the task of structural learning, in particular for k-local Hamiltonians. There are a few more technical caveats, but that's like the main structure you might imagine being imposed in a Hamiltonian. And they do some, a number of clever tricks to do this efficiently. But in principle, one might imagine that this can be done efficiently, say in the system size, simply because if you're assuming that your Hamiltonian is at most k-local, then there's only a polynomial number of terms to consider, assuming that k is some constant. And so there are two questions you might ask, that might violate this assumption. So one is, what if your Hamiltonian has L local terms for some L greater than k? So perhaps you assume that a Hamiltonian is k local, but in fact it's, say, k plus 1 or k plus 2 local. And so, maybe you have some interaction that's like this, that's spanning all of these qubits, and you don't know about it. Your assumption beforehand is just that, it's on this square lattice. So can you pick up this kind of term? And naively with their algorithm, you wouldn't be able to. More fundamentally, you might ask, well, what if, say, you knew L or even K, but that it's greater than constant. In this case, right, the number of terms you have to kind of check over is going to be a super polynomial, and in that case, you're kind of unable to do this efficiently from the get-go. So we want to consider precisely this kind of problem. We want to consider a non-local regime in which your Hamiltonian terms are not necessarily constrained to be, have constant locality. But we will consider it to be sparse in the sense that in its Pauli decomposition, we can assume that there are most a polynomial number of non-zero terms. Of course, if there are more than polynomial number of non-zero terms, then the description of this Hamiltonian is inherently exponential to begin with, so we can't imagine having an efficient algorithm. So the question is, can we still learn these kinds of Hamiltonians? One of the main challenges for doing this is that even though there are only a polynomial number of terms guaranteed to be in a Hamiltonian, you have to kind of discern them from a pool of exponentially many candidate terms, right? Because we allow the support of these Pauli operators of locality to be unbounded. You have basically the whole pool of like 4 to the n minus 1 Hamiltonian terms or Pauli operators to consider. So naively, you would have to sort of brute force check over all of them, which would of course be exponentially difficult. Okay, the main result, of course, of this paper is that it is indeed possible to do efficient structural learning for sparse non-local Hamiltonians. So essentially, we get around this brute forcing of all the Hamiltonian terms, all the possible Hamiltonian terms. So we have, in fact, two different algorithms depending on the kind of access model that you have for this unknown Hamiltonian. And one, we essentially allow time reversal access, which is to say we allow moving forwards and backwards for that unitary operator. So this is sometimes not always possible. It is possible in some certain settings, for example, perhaps like quantum simulation certification tasks, or tasks where you can assume some further structure in a Hamiltonian, like a chiral symmetry. Under this sort of access model, we get essentially Heisenberg limited scaling, where the evolution time you need, so the number of queries times the amount of time for each query, will scale as something like m over epsilon. Recall that m is the number of terms in Hamiltonian. And of course, the main important feature is that this is all polynomial time computation as well. So in instances where we don't have access to time reversal dynamics, and we only have access to the forward time dynamics, we have a slightly weaker result, but it's still polynomial time. So in this case, the evolution time scales as the norm of the Hamiltonian over epsilon, whole thing to the fourth power. So not as efficient as Heisenberg scaling, but nonetheless still polynomial. And the important crux of this work is that the computation time, so say the classical computation time needed to infer and deduce the structure of the Hamiltonian, is polynomial in the system size and in the inverse precision. So I'll pause for a moment and say that we're not, going to account for any like logarithmic factors, and all the complexities I state will be, leading order, big O notation sort of scalings. Okay, so let's compare this to the best known prior works before this paper. To my knowledge, the best algorithm that could do structured learning for the sparse non-local setting was essentially this paper by Matthias Caro. In fact, it had polynomial amounts of evolution time, which is to say that this task is not that informationally theoretically hard. Only a polynomial amount of, say, information accessed from the system allows you to learn this Hamiltonian in a rather straightforward manner. But the algorithm proposed would incur an exponential computation time. Essentially, you would have to just brute force check over every single possible Pauli operator and see whether or not that Pauli operator had a large coefficient in front of it or not in the Hamiltonian. So our main improvement is to remove this exponential time brute force algorithm. Okay, I'll take a quick detour into some results imported from the classical computer science literature, and just comment that our algorithm can actually be extended a bit more generally. You can think about it as a quantum Goldreich-Levin algorithm. So in the classical case, the classical Goldreich-Levin algorithm says if you're given some Boolean function, you can always decompose it into its Fourier decomposition as such, where you have Fourier coefficients, f hat sub s, and these indicator functions chi sub s of x is just like the Fourier decomposition of your bit strings. So the classical GO algorithm gives you a way to learn all of the large Fourier coefficients in this Boolean function. So given some tolerance threshold epsilon, you can essentially learn with high probability all of the coefficients, Fourier coefficients that are larger than epsilon in time that's only polynomial, say in the infinity norm of this function, so the largest value you could take, and also polynomial in, say, the number of bits and their position. Our result, it turns out, can learn the Fourier spectrum of any quantum operator A in time that's polynomial in the spectral norm of A, the number of qubits, and the inverse position. This is a direct analog to this result up here. And in particular, the way this works is if you're given a block encoding access to A, you can do this, you can run this kind of algorithm for any A, regardless of whether it's unitary or Hermitian or whatnot. So to compare this to prior sort of quantum GL analogs, most works have considered the case when A itself is already unitary. So this is important in things like Hunte testing. The case when A is not unitary, essentially, to my knowledge, has only been considered for k-local Hermitian operators, which is to say k-local Hamiltonians, and indeed in the context of these prior works on Hamiltonian learning. They assume that A is k-local, and this allows them to get a efficient sort of quantum GO type algorithm. And in our case, by sort of generalizing beyond the k-local constraint and allowing block encoding access to the operator, we can do a quantum GO type algorithm for any sort of operator. Okay, so now let's get into the meat of the algorithm. The algorithm is based on the concept of pseudo-choice states, which is introduced in this 2023 paper by Juan Castaneda and Nathan Wiebe. They proposed a Hamiltonian learning algorithm in which you learn the Hamiltonian through access of this particular resource state that they call a pseudo-choice state. What is a pseudo-choice state? Essentially, you can imagine a choice state is just you take a maximally entangled state and you send it through a channel that is, your unitary, say, or some quantum channel more generally, tensor the identity. A pseudo-choice state is similar to that, but instead of sending, say, a quantum channel, a CPTP map, you send through the Hamiltonian in some sense. So you apply the Hamiltonian tensor the identity onto this maximally entangled state, and actually they introduce what we'll call a pseudo-choice state with a reference, which means that there is some also reference state here on some additional insular qubit. And the purpose of this reference state is essentially to learn this normalization factor. So of course this state has to be normalized because your Hamiltonian is not necessarily a CPTP map or even a unitary map. But nonetheless, you can write down the state and you can ask, how can I prepare this state and whatnot? We'll get to that in a moment. We'll get to that now. So if you assume that there is some normalization factor delta, which is greater than or equal to 2 times the spectral norm of your Hamiltonian, then there actually exists a circuit which, given access to a block encoding of the Hamiltonian properly normalized, can prepare the state with higher probability, essentially with probability greater than half. And this is outlined in this paper. Essentially, it uses techniques from like quantum singular value transformations to implement. And that's all I'll talk about for here. You can see our paper or their paper for the details of this construction. But the main question is, how do I get a block encoding of the Hamiltonian, given I just have access to the unitary, which is an exponential of the Hamiltonian? And this requires you to take essentially what is the matrix logarithm. You have to use some sort of quantum signal processing to synthesize an approximation to the matrix logarithm of the unitary from access to controlled versions of the unitary. Now, once you have this pseudo-choice state, so I'm going to redefine it slightly here and just plug in the normalization by fiat, then estimating Hamiltonian terms is fairly straightforward. First you defined what are called decoding operators. So these are operators O sub A, which are basically some version of the E sub A's, such that their expectation with respect to the pseudo-choice state, in expectation, they give you, essentially the parameters, the coefficients of the terms in Hamiltonian up to some normalization. And so this delta is something that you pick. So you can easily, account for that normalization. The n is a normalization that is encoded in this Hamiltonian, and so you'll have to learn that as well. And that's the purpose for this sort of reference state here. You can define a reference decoding operator which learns the normalization, and using some propagation of error analysis, you can basically conclude how this sort of procedure scales. All of these things can be estimated efficiently using techniques such as classical shadows, which is essentially you apply random Clifford circuits to the end of this state preparation circuit, and you measure, and you construct certain estimators that allow you to efficiently estimate these expectation values. So the evolution time of this process, if you do through the whole error propagation analysis, looks something like this. Basically, the norm of h divided by epsilon squared. Okay. So let's recap this pseudo-choice state method. The pros is that you can learn m parameters with log m scaling. This is quite nice. It's very informationally, theoretically efficient. And in particular, there's no dependence on locality. Those decoding operators we defined simply use the Pauli operators E sub A directly in the definition, and it doesn't matter what locality they are. You can define a decoding operator for any Pauli operator you want. The cons, however, first of all, is that it requires controlled access to your Hamiltonian dynamics and also the time inverse. So it requires you to have access basically to controlled U and controlled U dagger. So that's what this is. And furthermore, it does not support structure learning of sparse non-local Hamiltonians, essentially because you have to define those decoding operators classically. And that requires you to know what are the Hamiltonian terms you care about in the Hamiltonian to begin with. So these sorts of these cons, which I'll call cons 1, 2, and 3, are disadvantages that our algorithm will seek to show up. Okay, so the first thing that we'll do is remove the need for controlled unitaries. This we can achieve through a technique that was actually already introduced called controlization. The idea of controlization is that if you're given what's called fractional query access to your unitary, which is just to say you can apply the unitary to some fractional power, then we can in fact approximate its controlled form. In our case, we have natural access to the fractional query access to our unitary simply by the fact that we can tune the time to be some fractional value. In particular, we're not really going to approximate the controlled form of the unitary itself, but rather the unitary generated by the traceless part of the Hamiltonian. And this is simply because, your unitary is invariant up to some unobservable global phase. And so without any sort of like additional information or additional reference, we really can't control that unknown global phase. Okay, how does this work? It's essentially the circuit that you see here. What you're going to do is pick some capital N for a number of like times you repeat this circuit inside here. And all you really do is you take your unitary, you say you want to evolve for some time t, and you instead break it up into chunks that evolve for time t over n, and you conjugate that evolution with controlled Pauli operators, where these Pauli operators are sampled uniformly from the set of all Pauli operators. What this does is it creates over the expectation of these random Pauli operators, it creates a quantum channel, and that quantum channel we can call this control U tilde. And that quantum channel you can guarantee to be, say gamma close in diamond distance to the desired actual control unitary. And it turns out that the number or the length of the circuit, so the number of repetitions you have to do, the n, only has to be order 1 over gamma to get gamma diamond distance error. And so this is actually quite nice if you're analyzing just the amount of evolution time that you seek, because if you want to do a controlled unitary for time t, actually your total evolution time is unaffected because you just do sequences of t over n duration evolutions n number of times. And so how does this work? Essentially, you can show this by sort of Pauli twirling arguments plus the Q-drift algorithm. All right, and so what does that mean? Well, we can import this controlization technique, taking care of all the various different amounts of errors that we need, and essentially we can remove this need for the controlled evolution of the time dynamics. So this shows up the first con that we had. Okay, next we'll get into the structure identification phase of the algorithm. So without knowledge of the structure, we need to do some initial phase that will learn what all the Pauli terms in your Hamiltonian is. To do so, let us introduce a referenceless variant of the pseudo-choice state, which is basically just the pseudo-choice state we had before, but we don't have this additional ancillary qubit that had this sort of reference state in it. And to prepare such a state, you can basically just take your original preparation circuit for the pseudo-choice state with the reference and just toss out the reference and don't control this block encoding. So one thing to observe is that you can rewrite this referenceless state as a superposition over all essentially these sort of Pauli states where the coefficient is proportional to the strength or the weight of the term in the Hamiltonian. So in particular, if you want to measure this state in this basis, you can do this efficiently simply by the Troy isomorphism. And all it amounts to is just Bell measurements across pairs of qubits. So what this means is that by doing Bell sampling on this referenceless pseudo-choice state, we get a distribution that is proportional to the size of the coefficients in the Hamiltonian squared. And with this, we can basically make two claims. One is that if the term in the Hamiltonian is less than, say, the epsilon you care about, then we can simply set that lambda to be 0. This is already an epsilon good estimate. And so otherwise, we just have to sample this referenceless pseudo-choice state some number of times until we observe all of the big coefficients, all of the terms that have lambda greater than epsilon. And basically, you can argue using some principles from things like the coupon collector problem that you can generate a set of Pauli labels containing all of these large weight operators using essentially like norm of lambda squared over epsilon squared copies of this referenceless state. So what this means is that just by sampling this referenceless pseudo-choice state in the Bell basis, it reveals its structure to you by itself. Okay, and the upshot of all this is that using just that number of copies of the state, we can in fact learn the structure of a sparse non-local Hamiltonian simply by running that phase first, learning all of the large weight parallel operators in your Hamiltonian with higher probability, and then using the first the parameter estimation phase with the Zhao tomography to learn all of the coefficients in front of those large weight operators. And because we're promised that there are only a polynomial number of terms in a Hamiltonian, there will only be a polynomial number of terms that you need to do Zhao tomography for. Okay. Finally, we ask, how do we get rid of the time inverse requirements? So recall that the technique that was used to block encode the matrix logarithm of the Hamiltonian, the matrix logarithm of the unitary, which is the Hamiltonian itself, required us to use techniques that are reminiscent of the quantum singular value transform. And essentially, this requires you to have access to inverse applications of the unitary. So we ask, how can we get rid of this requirement of the inverse to the unitary? It turns out that you can actually get nearly Heisenberg scaling by using some additional sort of quantum singular value transform techniques. We won't talk about that in this talk, just for the time constraints. But instead, we'll ask a kind of more interesting question: is that even if you're only given access to 4 time queries, can we still block encode H? Because if we can block encode H, then we can prepare all the pseudo choice states that we need, and the rest of the algorithm follows through. And this would bring our algorithm perfectly in line with the conventional learning access models. Okay, and so it turns out that in order to do this, you can actually appeal to a fairly conceptually straightforward idea, which is the matrix logarithm of an operator. All we wanted to do before was to construct by a polynomial transformation via the QSVT approximation of the matrix logarithm. But you can do this just by, say, a series expansion as well. And so this series expansion for the matrix logarithm is well known, and it converges as long as the norm of the thing in the exponent of your operator is bounded. And so, under this normalization assumption, which we can do just by setting the time again to be an appropriate amount, you can first rewrite this series expansion into a proper linear combination of unitaries, which is to say, this u minus I is not unitary, but you can just expand things out with, binomial expansions and so forth, and then truncate at some order k. Now, this gives us an approximation that we'll call h tilde, and this is a linear combination of unitaries that can be implemented with fairly straightforward techniques, essentially looking something like this. You have these sorts of canonical prepare and unprepared circuits, and then to implement the LCU, you do like controlled versions of each of the terms in Hamiltonian under this decomposition. And now this decomposition is just u to the positive powers of j. So these are just 4 time queries to u as sometimes j over delta. And it looks like this. Now, of course, you see there are controlled versions of this unitary, but each time we see a controlled version, recall that we can just use the controlization technique to turn these controlled versions into some sequence of uncontrolled unitaries conjugated by random pallies. So to do this, you pay some overheads, but they're not too severe. What's remarkable actually is that the number of ancillas that you'll need, so the size essentially of this like prepare register, will be scaling as doubly logarithmic in delta over epsilon. So they call that delta is basically order of the size of the Hamiltonian, its spectral norm. So this is like doubly exponential, doubly logarithmic in the inverse precision, in units of the Hamiltonian eigenvalues. And then as for the LCU L1 norm, which is sort of the cost that was required to successfully prepare a state that has, that applies this approximation to the Hamiltonian, that would be order delta over epsilon. And so in sum, skipping some details about how the error analysis propagates, we get the following time-forward algorithm. First, we can do structure identification in polynomial time, which is identifying all of the large terms in a Hamiltonian using just 4 time queries. And then we can use the pseudo-choice state method using Zhao tomography to learn all the parameters to position epsilon. And both of these routines take order, norm of h to the 4th over epsilon to the 4th time. And all of the classical post-processing computation is all polynomial. Basically, using this matrix logarithm LCU, which allows us to do this task with only 4 time queries, only incurs a polynomial overhead. And so finally, this shows up this final point of needing the time reversal dynamics of the unknown Hamiltonian. Okay, so in summary, let's recap what we've accomplished here. First is we've given a polynomial time algorithm to learn sparse non-local Hamiltonians, which is to say that we are able to learn some polynomial number of unknown terms in this Hamiltonian for which we are given only time evolution dynamic access out of a pool of an exponential number of terms. And we achieve this quite interestingly by applying some well-known quantum simulation techniques to the learning setting, which I think has a lot of potential in the future. And this works not only for models where you have access to the time inverse dynamics, which gives you faster query complexity, but also in the time forward convention, the time forward access model. So of course, there are many open works to be resolved. One is that this algorithm itself is arguably not very practical. It's a very interesting theoretical result, but implementing in practice might be challenging. So to that, I recommend interested viewers to check out these works. The second work in particular is also going to be presented in this session at STOC. And I think an interesting question is to ask, well, what does structured learning look like with Gibbs state access? So in this model, we don't have access to the time dynamics of the Hamiltonian, but instead we're given copies of the Hamiltonian's Gibbs state at some known temperature. There's a lot of work on the Hamiltonian learning from these sorts of Gibbs states as well, but to my knowledge, not that much work has been done on the structure learning part. And finally, I think the matrix logarithm block encoding that uses only time forward queries is quite an interesting result. And I'm curious to see, what sort of utility this has in other areas. So thank you for your time. Here's the funding offices that made this work possible. And again, if you're interested in the full paper, please check it out at this archive link here. Thank you for your time.